So let's look at a typical function. I'm going to let this function be y equals x squared. And as we know, this is a parabolic function where it looks like this. So to really answer the question about why the slope of a function doesn't necessarily have to do with its derivative and why they're not always equal, let's first talk about what slope even means, right? We're stepping a little bit back to before calculus and what you learned, because there's a particular property that many of us are overlooking and why we're making a mistake in our understanding here. So if I wanted to find the slope between these 2 points for the function y equals x squared. So here are your x values, and here are your y values. When x is 1, we know that y is 1. When x is 2, y is going to be 4, right? Because 2 squared is 4. And if I asked you, okay, for those 2 points on this graph, if you were to connect a line between them, what would the slope of that line be? Well, we know that for slope, we talk about rise over run. And so you would basically take this y value, 4, minus the original y value of 1, all divided by the same idea, but now subtracting the x values. So 2 minus 1. So the slope of the line connecting the points 1, 1, and 2, 4 would basically be 3. But that doesn't say anything yet about the derivative. And also, here's what you're overlooking. The reason why we were able to find the slope between these 2 points right here is because what's really important to understand, we have an interval. An interval of what? An interval for x. So this interval is basically saying, hey, when we found the slope of the line going from 1, 1 to 2, 4 in this graph, the interval itself had this width right here, right? X equals 1 on its left and x equals 2 on its right. Meaning the interval itself has a size of 1, the difference in x. Now, I know this seems very elementary, and you might be wondering, what does it have to do with the derivative? Well, hang on for a second, because now let's pivot over to how you learned about finding the derivative in calculus, and why then does it not equal finding slope? So I'm going to go back to that same function, y equals x squared. And after drawing it, we're going to talk about one of those 2 points. Now we're going to talk about the point 2, 4. So this is your 4 value. This is 2. And I want to know, what is the derivative at the point 2, 4? So in other words, when x equals 2, what does the derivative look like? Is it a slope? Is it a point? Is it defined? Well, remember how you find it, right? Theoretically speaking, to find the derivative, when x equals 2, we take the definition of a derivative itself, which is a limit where the difference in x approaches 0. And I'm actually going to call this difference h. Of f of x plus h minus f of x all over 2. And we know in this case, okay, x equals 2, right? So I'm going to put that little disclaimer right here. So what you would do for this limit is you would plug in x equals 2. And what we're trying to do right now is we're trying to bring this h, this difference in x value, super, super small. Basically, as a theoretical limit, as if the interval had a size of 0 at x equals 2 itself. And this is where many of you are getting tripped up. Because remember, for slope is rise over run. But at a point, if the width of your interval is 0, because at a point, the x value doesn't change, right? When you do subtraction here, you would be dividing by 0, which is not allowed. So then why does the derivative itself work? And why is that defined? And the reason is because we express the limit as the definition of a derivative, because really what you're allowing yourself to do here is you're talking about convergence. You're taking this h value and you're converging it to a difference in 0. And if you look at y equals x squared at x equals 2, so say right here x equals 2, if I were to zoom in here, what you're basically saying is, okay, at this point, let's talk about this idea of a neighborhood of a point. The neighborhood is an area around the point that is super, super, super close, where you can kind of think of this area as having an interval for x that has a negligible width. So basically, you would have your x1 and x2 values, and you can think of it as almost like, hey, this one is a 2, and then this one's a 2.000000001. And the reason why it helps to think of the derivative this way is because if I then wanted to draw a tangent line, it would kind of guide me into actually being able to draw it around a point. So for example, in this case, the tangent line would look something like this, right? Which gets me into that bonus tip that I was going to tell you about. And by the way, before I get to that, if you're enjoying this video and you really want to see more tips on your math exam, smash that subscribe button. And you can also check out my game I made for you for free called Number Ninjas in the description below if you want a fun break between your studying. So now what I want to look at is, okay, so we have this interval for slope. We don't really have an interval for a derivative, but what is the derivative talking about? And here's the key difference. Slope involves rise over run on an interval of x. However, the derivative is instantaneous rate of change. Think of it as driving your car. If I made a really cool movie of you driving your car and I froze the frame at a specific time and I looked at your speedometer, it would tell me something about how fast you're going, right? Now, if I freeze it, you didn't go anywhere because you're frozen, but it would tell me that if I were to let the video run at 0.1 speed, I can get a good idea of the distance you've traveled, right? Because I know what your instantaneous rate of change is going to be. And that's why with the derivative, we are able to draw that tangent line. Because yes, there's no interval at a point, but it tells us at an instant that if we were to let time go on, what the rise over the run is going to look like, assuming there's no change in behavior of what's happening with the function, right? So then what does a tangent line have to do with all this? So going back to y equals x squared, so at x equals 2, if I draw this tangent line here, because we know, for instance, that the derivative of y equals x squared is 2x. And for x equals 2, this has a value of 4. And I should actually call this dy over dx, or y prime. So y prime is going to be telling you that when x equals 2 in the original function, because the derivative gives you instantaneous rate of change at a point, when x equals 2 in the parent parabolic function, y prime having a value of 4 means that this tangent line happens to have a rise over run that is 4. And you can actually find what the equation of that line is. And so, again, that does not mean that the tangent line equals the derivative. The tangent line itself, by definition, is a line. The tangent line has a slope because the tangent line is of the form y equals mx plus b, where m is the slope. But it's a different definition than the derivative. The derivative helps us to determine what the tangent line looks like at a point, but they're not the same. So I hope this video really helped your understanding with what you're learning in the beginning of your Calculus 1 class. And if you want some more practice for your Calculus 1, be sure to check out this video.